That's where we stopped yesterday. I'd like to discuss with you two results which directly follow from Baltzano-Weierstrass we discussed yesterday. One of them called minimax theorem, and the other one is the other one, you know the name at least. It's called intermediate value theorem. So minimax one says this: if you have a continuous function of several variables, but the one which takes numerical value, so here we don't have a vector in the codomain. If it is continuous and if it lives on compact subset, like it is said in the statement, then there will always be points, 2 points, maybe more, on which your function takes the max and the mean value across the compact subset K. And that's what is said here. You see there are points x, which I called x min, and the point x max from K, such that at x min we getting exactly the minimum value of my function. At x max you're getting the maximum value of your function. That's the first result we need to know. That's right. And the second one is the intermediate value theorem. This time, so before this, the minimax theorem, you need two important assumptions: continuity and compactness of a subset. For the intermediate value theorem, in multidimensional setting, in the setting of multiple variables, you need the assumptions continuity, as before, compactness, and plus path connectedness of the subset. If you have these assumptions, then you can basically claim the same as you claim for the function of one variable. Function takes every intermediate value. So whichever value you take between max and min, and strictly speaking, this x should be typeface with the boldface. I mean, it's a typo, because we normally use I normally use boldface for the vector quantities, and this one obviously not a boldface. So if you make this correction, if you take any value b between min and max, there will be a point within K which delivers exactly that value. Right. All of the assumptions in both theorems, so in the preceding theorem, continuity and compactness, they are important assumptions. If you drop either of them, the theorem is no longer true. The same is true about the intermediate value theorem. All three assumptions are important. If you drop either of the assumptions, if you drop the continuity, path connectedness, or compactness, there in principle you will be able to come up with a counterexample to the theorem. And in fact, in this PDF file, there are some examples. I'll show you them. I'll show you these examples to you. That's right. Let's just go here. Here they are. For the minimax, it's three examples on a diagram. They even work in a one-dimensional setting. You see, that's a perfect example. You see the domain is compact. It's bounded and closed, and you both have the max and the mean attained by the function. Max is here, mean is here. Here you see you ruin the on this diagram you ruin the continuity. You see the function has a drop, this point of discontinuity at this point, and then the max value, well, the supremum of that function. It's better say supremum because this value is no longer attainable, right? This limiting value, the highest limiting value, it's no longer, there's no point for the function anymore to take that value exactly. So that's what you see if you drop the continuity. This is no longer true. If you drop the compactness, here's the interval, you see where you remove the endpoints, and by that you're ruining the compactness of the interval. If you remove the compactness from the assumptions, again you can come up with a counterexample. Here it is, this point, which before was the point of minimum, and it was part of the interval, but this point is no longer part of the interval. That's why, again, the minimum value this time is not attainable. That's the counterexamples for, I mean, that's just the demonstration of the two assumptions in the min-max theorem are important, continuity and compactness of the interval. That's a demonstration that the assumptions of intermediate value theorem are also, all of them are essential. You can't drop either of them. That's the classical setting, right? You have a function which is continuous on the compact and connected, path-connected subset. In that case, every point within this red interval is attainable. Every point is a value of some point, is a value of the function at some point. Here, on this diagram, you ruin path connectedness. You see, you remove the point from the interval. Now you take this as one single domain, these two separate subintervals. They are no longer path connected because you remove the point. And you see my function doesn't take all of the intermediate values. This interval, which is all covered by intermediate values, between some larger value, some lower value of the function, they are no longer attainable. And that's where on this function, on this group diagram, you ruin continuity. You ruin continuity, and again, intermediate value theorem is no longer true. Yeah. Now there's one example on the next slide here, which basically gives you the idea how you can prove intermediate value theorem in n-dimensional setting. Here's the example. It's sort of like a, oh, okay, let's just read the example. Prove the temperature above, prove that if the temperature above zero somewhere on the Earth's surface and below zero somewhere else, then there must be a third point where it exactly is zero. This is a perfect setting for the intermediate value theorem. There's a point where a function takes negative values. There's a point where a function takes positive values. The question is whether my function takes the zero value, which is in between negative, some negative and some positive. Before you can conclude that there is such a point, you have to check three assumptions of the intermediate value theorem: continuity, compactness, and path connectedness. Continuity, well, I guess the temperature, we assume that temperature across the surface of the Earth is distributed continuously. It's sort of like a natural assumption we make about the universe. Earth surface, sphere S2 is path connected. That's right. And it is compact because it's bounded and closed. That's why we do have such point. That's right. We do such, I'm sorry. That's why we do have such point. It's a consequence of the intermediate value theorem, because the function, temperature function, lives on a compact path-connected subset and it is continuous. However, the rest of the slide actually explains it, except of the rest of the slide link this result to the one-dimensional. Look what it says. I forgot what it says. All right, so what it says is this, actually. It just gives you some, I said it correctly, it just gives you the idea how to link the multivariable version of intermediate value theorem to the one-dimensional. What it says is this, look at this. It takes this path-connected and compact set sphere, applies a temperature function to it. As a result, it will be some subset in one dimension, because it's a numerical function. By the theorem we discussed yesterday, this image must be both path-connected and compact. So it will be some sort of interval. That's the only choice for the compact and path-connected interval on the line. And because we have both negative and positive points, there will be zero within this interval. Yeah. These lines, these three paragraphs, the last three paragraphs, you don't need them if you just refer the multivariable version of the intermediate value theorem. These three paragraphs, in fact, they indicate how this multivariable version of the intermediate value theorem is linked to the one-dimensional version of intermediate value theorem. But Jonathan Kress did this, why not? Right then. Any questions? Now, with the first theorem, with the first one, that's what I said on my slide. I mean, I updated my handouts a little bit. I said it exactly here. The intermediate value theorem, the proof is explained by the example in the J, Kress, MM, and IV theorems. In this PDF file I just showed you, in these 3 last paragraphs, they basically explain the proof of the IV theorem in multiple dimensions. MM theorem, the min-max theorem, for that theorem, I'll show you the proof. It's a very nice short proof. Basically, Balzano-Weierstrass from yesterday, it does the job there, and it's a nice proof. Look at this. So here's my min-max theorem. I have my function, which is continuous, and k is compact, and actually that's, yeah, well, it must be well, obviously it must be non-empty, otherwise it doesn't make much sense to consider function on empty set. You can, of course, do that. You can consider function on empty subset, which is compact, of course. There's no argument about that. But on that subset, obviously, function doesn't attain max and min. So look what the proof says. I'll take the supremum first. So I'm going to prove the half of the theorem. I'm going to show you that the max point exists. For the mean point, there are 2 options. You either can repeat the argument or reduce it to the first part. I'll discuss that. So let's just see why the max point exists, why the max is attainable. So first I take the supremum. I hope you still remember what's the difference between supremum and the max. Supremum is something which may not be attainable. It's sort of like an upper bound, which is the ultimate upper bound, the lowest possible upper bound. Right? That's what you studied in the first year. Did you? Great. So I take a supremum. I give a name to the supremum, M. Now I'd like to just show you what the supremum is. I'm just going to recall the definition from the first year. The definition says it has 2 parts. Number is called supremum for a function if, on one hand, this number always dominates the value of a function. It must be an upper bound for every element. So for every element in my k, the value of my function never exceeds this m. That's the first part. That's the easier part. The harder part, it involves the harder part. It says also, for every positive epsilon, I can find a point in my set, which may depend on epsilon, and I reflect this dependence by the subindex epsilon. You may find a point such that the value of the function get very close to this m. So on one hand, m is the upper bound. On the other hand, values of the function, you can bring them as close as you wish to your m. Still below, but still as close as you wish. That's how you put it in plain English, the second part. Now I'm going to make a choice for this. It says here, for every epsilon, there is a point like that. I'm going to make a choice of this epsilon. I'm going to choose this epsilon, 1 on n. N is an integer, positive integer. For this epsilon, there must be some x, which depends on that epsilon, and this time I will call it xn, because eventually it depends on this index n, which makes this property true. Well, I will combine this together with this property, and I'll put it in one line like this. So the definition of my supremum ensures, once again, that if I choose epsilon 1 on n, there will be points, x sub n, with this property. Look what I'm going to say now. That's the place where we're going to use the Balzano-Weierstrass. It's a typical way how it is used in lots of results in analysis. Right, Weierstrass, this sequence, we don't know much about it. But Balzano-Weierstrass ensures that I can find a subsequence, which I gave another name, yk. You see, x and k. I can find a subsequence such that this subsequence, it has a limit. The whole sequence, it may not have a limit, but there will be a subsequence all the time by Balzano-Weierstrass, which is converging. This is because my set is compact. And now I'm going to forget about the rest of the sequence. I'm going to focus only on this subsequence because it has this extra property. It is converging. So what I'm going to say now is this. I'm going to write up this for my subsequence. Well, first I'm going to say because f is continuous and this sequence is converging, the value of my function taken on this subsequence only, they will also converge because of the continuity. Continuous functions applied to the converging sequence returns the converging sequence. So these values, they will converge to f of a. That's a continuity assumption. And now if I take this, I called it asterisk. By asterisk, this value m must be this f of a, right? Because the sandwich principle. This number, if you push n to the infinity, or if you push, if you push n sub k to the infinity, this goes to m, this is just m, and these values taken over subsequence, they go to here, to f of a. So by the sandwich principle, this f of a we just found, it must be m. And here we go. I took the supremum, and I presented you the argument which shows you that there is a point, a, at which this supremum is attainable. That's why the supremum, as a matter of fact, is max. And as a choice for my x sub max, as a choice for this point, I can take this a we just found. And that finishes the proof. That finishes the proof. So. Any questions? If you want to see the second part of a theorem for x min, you either can follow similar steps, although you will need to replace the supremum with the infimum, or there's a nicer trick to do that. Do you know the trick? How we can link the existence of mean to the existence of max? Yes? That's right. We can take another function, g equal negative, like this. And then the max for one will be mean for the other. That's a good trick. And if you use that trick, you can ensure the existence of max and mean at the same time. So you don't need to repeat the same steps for the second point. Thank you. That's good. Thank you. All right. If you don't have any questions, I go back to my main set of slides. These ones. All right. We move on. We move on with our sort of transfer of the things we know about the function of one variables, the function of many variables. Now we're going to discuss with the differentiability. With the differentiability, there are more differences with the one-dimensional setting in comparison to the continuity. First, I'd like to analyze with you what we call a differentiable function in one dimension. That's exactly this slide is exactly designed for that. So in one dimensions, last year, you call the function differentiable, function of one variable, like in here, at some point a, if you had a limit of this type. If you had a limit of this type, you call it differentiable. And then for this limit, you introduce a notation f dash of a, and then you discover the algebraic properties, many other properties. But at the beginning, that's when you call the function differentiable. L was a derivative, and you had a symbol for that. Now, I'd like to transfer this to many dimensions. Like when you have a function which takes multiple variables and takes values in vectors. How can you do that? Well, if you saw my handouts, my question probably will be redundant, or maybe it won't be. So to do that, I mean, if you saw the next, you obviously, most of you saw the next slide, and then you know what I'm going about, what I'm about to say. But before to see this link between this definition and the one which will be on the next slide, first I need to restate this claim that the limit exists. What I do is this, look at this. I just take this L on one side, bring it under the limit, and then I combine these two in one single fraction, and that then ends up like this. It's some elementary manipulations, but this is the starting point for the n-dimension setting. Because I'm going to take this last equivalent statement of differentiability in 1 dimensions, and I'm going to take it to multiple dimensions. And that's the way it is done. Look at this, how it is done. If you take a function of now many variables, which takes values in vectors, I'm sorry, you claim that I claim that the function is differentiable at some vector point A if and only if. You see, my L, which was a number before, is replaced by a matrix of dimension, appropriate dimension, m rows, as in here, and n columns, as in here. And what I require from this matrix, in order to call it the derivative of my function, I require these relations. And these are no longer numbers, so I no longer can consider this as a numerical sequence. That's why I put the norm, or length, or distance around it, and then I end up with the numerical sequences, and I can see if it's 0 or not. It's a very difficult definition what I say is this. Verifying that the function is differentiable, by definition, it may be rather tricky. Because it's about limits in multiple dimensions. And if you did questions today, and by now everyone was through the tutorials this week, the way a few questions about the limits in the tutorial set, if you did those questions in the tutorial or independently, and I strongly hope that you did, and I encourage you to do them if you haven't so far, you learn by now that every time you argue a limit, it is linked to some inequalities. I tried to make this very explicit by giving you hints with inequalities. Without those inequalities or some other inequalities, you will never be able to argue the limit. Epsilon and delta, which you say or write around your argument, it's always just a wrapping. The actual idea comes from the inequality. And finding that inequality may be a tricky business. So the same applies here when you argue differentiability directly by definition. It's a question about the limits in multiple dimensions. So it will require some inequality. And I repeat again, in finding that inequality may be a tricky business. In this topic, every time there will be questions arguing directly, differentiability directly, I will hint you the inequality, which means I will take the weight, significant weight, mathematical challenging weight of the solving those questions on me, making your life easier. Because it's not because the point of this topic or subject is just to explain to you this how it happens, not just to sink you if you can't discover the inequalities. But you have to realize finding those inequalities, it's an important part of the analysis. Right. I think we have a few examples where differentiability can be argued directly. First one is easy example. It's a linear. It's notations first. This matrix L, we're going to fix this notation for this matrix D sub A F. So it's derivative of a function F, or map F at the point A. Okay. Thank you very much. Okie dokie. First example is a linear map. Linear map from the first year. Remember, linear map, it's something which is given by matrix multiplication. Here's a map. You just multiply your multiple vector variable by a matrix A. This is a differentiable map. You can check this one, you can check instantly via definition. You just check this limit. Of course, when you check something, or when you check that the function is differentiable, you have to have this first guess what will be the derivative. Making those guesses, we have some rather streamlined way of doing that. We will discover that very soon. But for this one, I'll make a guess for you. So for the linear map, this L matrix, which is needed to be presented in order to convince someone that the function is differentiable, it just will be this A itself. And that is why, because if you take this limit, which appeared on the slide before, if you sub it in place of L, you sub your A matrix, these two, f of x and f of a, just simple matrix multiplication, you can eventually this are just 0, and that's why the limit is 0. Yeah. And that's the end of it. I have one extra example on the other slides, on the dynamic slides, which shows you another example of function differentiable. There's another example on the next slide right in here, but I don't like that example. I'll tell you why in a second. First, let's just look at this example. It's another direct example of differentiability, not as straightforward as the linear map, but still a relatively easy example. Look at this. That's the function I'd like to consider. You see the function sine x squared plus y squared on x plus y squared. So it's a two-dimensional setting, function of two variables. It is defined everywhere except the origin, because in the origin we cannot divide by 0, but I explicitly define my function at the origin as well. I just say it will be 1. Some of you may guess even why I say so. So I claim that the function is differentiable in the origin, at the origin, sorry. And I give the choice for the derivative matrix. This time it's a matrix 1 by 2. It's a row matrix. And the matrix will be trivially 0 matrix. So here we go testing it. Testing this limit in the definition of the derivative. Look at this. I have to test is the limit given in like a completely, I mean, I just gave you the complete limit. We have to test is a question mark saying that we have to test this limit. We have to convince everyone that this is 0. Boldface x, boldface 0 here, it's this, and this multiple variable vectors. So I need to test this limit. If I can convince you this is 0, we're done. For the linear map, it was easy because the whole numerator was just 0. Constantly 0, no problem. For this function, well, I'll make substitutions. Here's my substitutions. I skipped a few arithmetic steps. The denominator here, x takes 0, and length, it's exactly this value. And the numerator, this one 0, because L is a 0 matrix, and this difference, it's right in here. Question mark, because it still needs to be argued. We need inequality, and here's my suggestion for the inequality. That's the one probably you saw in the tutorial set, because this inequality I suggested once already. This inequality. If you believe in this inequality, and I didn't ask you to prove it, it's the first year stuff. Some of you may attempt this. For this presentation, we just need this inequality. If you believe in this numerical inequality, if I use this inequality, and I use for the a this value, x squared plus y squared, let me just call this a capital, because I don't want to rewrite this again. I don't want you to rewrite it again, so we introduce this abbreviation. I call this number in brackets a capital. Then if I use this inequality, this number in brackets can be controlled like that. Right? It's a squared and 1r. Yeah, that's a squared. Why does it say 4? It's a typo, obviously. It should be square, which means this is the distance of x degree 4. And so if I try to control this whole expression under the limit, yeah, it will be like this, with the correction for the typo, of course. Because absolute value of a is controlled by this value, the denominator is just one single length of x. X is here. So if I need to conclude that the limit of this expression is 0, here's my sandwich principle again. Left-hand side is constantly 0, right-hand side vanishes because of this. So in principle, you can now wrap it up into epsilon delta presentation. You can say for every positive epsilon, there will be delta, which will be cubic root of epsilon, because of that part, right? It will be cubic root of epsilon, such that the one is true if the other is true. If you've been through the limits questions in these tutorials, you know what I'm talking about. Inequality is the key of every limit argument. Epsilon delta, it's nothing. It's just the lines you say every time. And that's why the function is differentiable. Any questions? Like I said, every time you argue your limit in this topic, I'll try to hint you the inequality. Yeah, I'll try to hint you the inequality because it's finding those inequalities is not a part of the skills we'll try to discover in this topic, learn in this topic. But some of you may even come up with inequality, which is good. Now, there's another example on this set of slides. This is the example. Another function. It's the one which takes two-dimensional vectors to two-dimensional vectors. Again, you see the choice for the derivative is given to us. The choice for the derivative is given to us. And Jonathan Kress tried to verify the limit. The reason I'm not completely happy with this example, I'll tell you. He just does the same thing. He just computes this expression in a numerator. Here it is. He computes the then he puts this expression into the limits. That's the length of this vector. In numerator vector, that's the length of the denominator vector, x take a. And then he says, this is true, but that takes a bit of work. That's what I don't like about this, because he didn't show us the inequality which works in this limit. And discovering that inequality, that's that work of the true analyst. The rest is just some elementary steps everyone can do after a while. There won't be such examples in my tutorials, trust me. In my tutorials, I want you to see the essence of the question. I will give you the inequalities, but you should know where to put these inequalities in your arguments. Well, I hope so, it won't be, because I didn't check what sort of questions from the last year we had in relation to differentiability. I didn't look into that. But I do some revision of questions before I release them. I'll try to avoid these sort of questions. Any questions? All right. Well, it was a part of the Jonathan Kress setting of the slides, this result, which says that every differentiable function is continuous. There is a proof for that. It is a short proof. I think we will, for now, I think we'll skip that. I will publish the proof. I mean, if you follow my upload, before I come here, I just made the uploads for yesterday's lecture. And everything I promised to publish, I published. This one will also be published in due course. It's a relatively simple proof. I'll make the publishing. I may include this in the tutorial set, but it's not going to be marked as R, as recommended. But if you're interested in seeing that proof, yeah, I will publish that. Yeah, well, that's a good thing to know. That's every differentiable function is continuous. And we're going to just move over. That's the file which I'm going to publish. Partial derivatives. This is a subject which is more closely linked to the first year. And our main objective in discussing this, and that's what we're going to discuss, is, well, first we're going to just link this to the first year. And secondly, our job is to link this to the differentiability. Because differentiability, as we just saw it, it's way different from the first year. It's way different. It's a limits, it's inequalities, it's thinking process. It's not a routine. You can just, there's an algorithm you follow step by step. You don't have to think at all. In a differentiability, you have to show your power as an analyst. In the partial derivatives, you don't. Computers can do that. They're not analysts, computers, right? Take Maple, take MATLAB. They do derivatives, but they can't do differentiability. You won't be able to do that. Because differentiability, it's a human job. For the true minds. Partial derivatives, it's a monkey business. Forgive the expression. But still, we have to discuss that. And there's a link between the partial derivatives and differentiability, which on many cases makes things really easy. And you will see that link. You don't like monkey business? Oh, my back hurts. So partial derivatives, it's a very simple concept. If you know derivatives from the first year, all you have to do, you have to treat your variables, one of them fixed, and just only one of them is changing. So these diagrams of Jonathan Creste explain it really well. That's why I kept them. I just do it separate files because this way the structure of the lecture notes is better seen. Plus, when it's different files, you don't have to download one single 13 or 20 meg file and then look through all of these pages for the content you need. That's one of the reasons I split things into this tree-like structure. Anyway, so if, for instance, it's for the function of two variables, if you compute the x partial derivative, so you fixed one of the y's, so geometrically you take sort of like a slice for the function, and you compute this derivative of one-dimensional function which is attached to that slice. That's all you do. So you keep one variable fixed, the other one is the one you differentiate against. Yeah, there are a few that's notations you have for the partial derivative. All of them are quite standard notations used in many books and in many questions, and you're free to use any of that. d1 of f, derivative with respect to the first variable. 1 means first variable. f1 of ab, fx, naming the variable. This is the d notation, df by dx, even though this time we use this curly d, not the upright d. Be careful with that if you write. And that's the actual definition. You see, you increment your first argument, and you divide by the amount of increment and see if the limit exists. That's all there is to it. The second partial derivative, when you just swap the rows of the variables around, you fix your x this time. It's another slice of totally different shape it may be. Now y is a free variable, the same definition applies, and the same similar notations apply as well. So d2 meaning second variable, df2 meaning second variable, fy, sometimes it's convenient to name the variable rather than to index it. And that's d notation, df by dy, and the limit, the actual definition. So all of this is just notations. This is the actual definition of it. Because the definition actually doesn't differ from the one-dimensional case. Computing the derivatives, it's all you know from the first year. You just transfer this literally to the second to this setting, and you use it. So there are a bunch of examples on the slides. For instance, well, it's a function z or f of two variables, partial derivatives, all of them here, like dz by dx. You differentiate this term, keep thinking of y as just a fixed number, so double xy. You differentiate this term, no y is 3x squared. You differentiate this one, which is a constant, that's why it disappears when you differentiate with respect to the x. Similar logic, but now the variable swapped over for the y variable. Here, it's a linear function in terms of y, that's why derivative x squared. No y here, it's a constant, that's why it disappears. Exponential, we know how to differentiate exponential, double e to y. That's another example. You can look for this. I'll publish this file. You can look for this, but you will have plenty of opportunities to do this. It's really boring, tedious exercises of this type. But yeah, if you like them, you'll enjoy it. Well, this last example on the slide is just a function of free variables. I think that the purpose of this line is just to show you that when you have free variables, the same logic works. When you name the variables with different letters, a, b, c, rather than x, y, again, the same logic works. You just change the symbols in the appropriate places, right? It's a very straightforward thing. You don't have to think at all. It's not the analyst's job. It's, I don't know. You can teach this like everyone, even the computer, to do that. Small notations. Actually, it's a second-order partial derivatives. All you have to know here is just partial derivatives by themselves. They are functions of multiple variables, and then you can differentiate them once again. If you do that, you will end up with a second level of partial derivatives, And this slide just gives you the type of notations we use for that. For instance, if you treat your df by dx as a function of multiple variables, and you apply your derivative once again with respect to the x, that's the sort of notations you may expect for that. D notation, d square f dx square. Pay attention to the position of number 2 there. It's like I said, it's a very simple, trivial thing, but well, in this topic I'm not sure, but in the other topic somehow people manage to put this number 2 in the wrong position. And sometimes it annoys the people who mark things. So, because such a little rule slips somebody's mind. Yes?
The square in the denominator, does that refer to just, for example, in the first one, the partial differentiability, does that refer to just the x or the delta x?
Well, it refers to dx, yeah. Yeah, but symbolically, this, you don't have to put the brackets around it. No, you don't have to do that. But conceptually speaking, yes, it refers to d. dx applied twice, yes. It's shorter notations, f double x, all numerical index notations. All of them may appear. Some of them, sometimes this one more appropriate, sometimes this is more appropriate. You will see that. Yeah, this is just the definition of partial derivatives in case you have n variables, the same definition as before. That's an example of the second order partial derivatives. I'll skip all that. Oh, well, it's a good thing here. So on this slide, it was made an effort. I mean, the effort was made, and second order partial derivatives were computed. Altogether, we have on the first look we have 4 combinations, right? xx, xy, yx, and yy. But on this slide, these computations show that when you compute the mixed derivatives, you see, when you x, y, yx, result is identical. Most of the time, this will be true. Mixed derivatives, so derivatives when you just take the x, y, or you take the variables of different combination, every time they deliver the same value, as long as you have the same amount of variables there. And that's actually what people know as, I don't know how to pronounce that name, but it's a French mathematician, Clairaut probably, Clairaut theorem, let's just put it like that. And it says that the mixed partial derivatives, they're always the same, and that's the conditions which ensure that when these derivatives are continuous, not at the point, but around that point. So if you have a point and you have an area around that, open area, like an open ball, and your derivatives are continuous across that open ball, then you can expect that derivatives are identical. Strictly speaking, from the mathematical point of view, we need to see the example where they are not identical in order to convince everyone that these conditions listed in this Clairaut theorem, they are important, they are essential, so you can't just say all the time they are identical. And there is an example on this slide which shows that. That's the example of a function. This is the example of a function given like that, which has second order mixed partial order second order mixed partial derivatives not identical to each other. Yeah, well, I think the next slide actually does the computation. Let's just look into that. That's a standard example, and Jonathan Kress put the computations here. So look at this, what he says. It's a lengthy computation, as a matter of fact. So before we can even compute the second order partial derivatives, we need to compute the first order partial derivatives. And given that the function is defined in these 2 different clauses, sometime we need to follow the definition of the derivative. Look at this. So what he says is this: if you compute fx and fy derivatives, first partial order derivatives, for any point which is not the origin, we can just use the first year stuff. We just compute this by the rules of differentiation, and that's the computation. I'm not going to verify that. And actually, you don't have to verify this on a piece of paper if you don't like. You can use MATLAB to verify that. I'm quite happy with that. Now, at the point 0, first order derivative requires definition by, computation by definition. We have to take the limit of this type. We have to increment the first, like if we go fx at 0, 0. You have to increment the first variable, subtract the value of the function at the origin, and divide by the amount of increment. There is no any other way to find the partial derivative at the origin for this function. Well, he does so. He does so because y is 0. This numerator is 0 all the time. It's the numerator in this computation constant is 0. The limit is 0. Similar evaluation for the y derivative. Again, by definition only. There is no any other approach. The value comes up now 0 again. This is the first level of computation. It's the first order derivatives. Now we're ready to go to the second order derivatives. First order derivatives, they also functions given by two clauses. First clause says fx equal to this if point is not origin, and fx equal to this if point is origin. It's not said here explicitly, but that's what it is. The same story for the y derivative. So here we compute fxy. We take fx, increment the second one, even though this time you see Jonathan Krauss didn't put here 0 plus h, but effectively it's here 0 plus h. You increment the second argument and divide by the amount of the increment. Well, if you use the formula for the fx, which is here, he did so. That's the evaluation, and he ended up with -1. If he does, now he does the similar evaluation for yx. This time he takes the fy derivative from here, from this line, and increments the first argument. He does the computations, and he ends up with 1. You can verify all these computations. We can trust him. I did this myself when I was a student, and I know this example since then. Now you also know this example. Any questions? It's a very freaky example. Most of the time you won't see that. Most of the time the setting of this Clairaut theorem will be satisfied, because most of the time you will be looking at the elementary functions. Elementary functions continues everywhere where they define, so you won't have any problem with this. But sometimes you can do that. And by the way, I asked you the other day, do you know the examples of non-elementary functions? Here it is. That's the example of non-elementary function. It is elementary on some domains, but altogether it is non-elementary, right? Because of this double clause definition. Oh, the time is up. Oh, almost up. Just I know you want to rush towards the door. Just give me a few seconds, and I'll let you go. Any questions? If you don't have any questions, let's just look at my main set of slides for 30 seconds, and then we'll be done. I just want to see what's the next. Actually, we're very good. We're very good time-wise. Thank you very much. It's not an easy hour to listen to a lecture of this level, but thank you very much for your patience, and you're free to go.